All right, welcome to another live stream where I want to kind of cover the topic of implied domain with some different types of functions. So what we're going to do in this live stream is basically kind of work on finding the domain of a function, basically the implied domain. And we're going to work through a couple different examples, basically look at, some functions, mostly with radicals, rational functions. And then we'll also go ahead and talk about how to identify the discontinuities of a function. And then we'll also work through some multiple choice kind of questions to prepare on that side. And then I'm not going to get through the, challenge problems, but I'll at least present them to you so you can kind of, see, what you would do as far as what we've learned today, if you can go and tackle those challenge problems or not. So the way that this live stream is going to go is kind of similar to what I did last week. Is I like to kind of work through this homework kind of sheet, all in once. And then what I'll do is I will take some time. If I have a little extra, I plan about 30 minutes for this live stream. So whatever extra time that I have, I will go ahead and, answer any questions that I can for you, or see if there's anything else, any kind of general questions that you guys have as you're joining along. So let me just push that. Oops, let's move that over. How can I move that? All right, perfect. So, all right, we are all set to go. So let me go ahead and get started here for the initial just kind of skills that we need to as far as identifying the domain. And then we're also, very important, going to be writing this in interval notation, because there's many different ways we can represent domain, but the more common method that we're going to use in this class is going to be interval notation. So, all right, let's go ahead and get started for example number 1 as far as determining the domain of the function. And in this example, we have f of x equals negative 4x cubed minus 1. Now, in this case, we're not going to be looking at the graph at all. But the idea of, the domain, remember, is the set of all x values that are defined for the function. And when you look at the graph, you can basically see, for basically how far left or how far right does the graph go, and then kind of not including any discontinuities, any holes or any asymptotes. Well, when we look at this kind of function here, basically, remember, a function is you have an input and you have an output, where the input values represent the domain. So we think about, really any numbers that we can plug in for x where we're not going to get a output, or that we're going to get, two of the same, two different outputs. In this example, every single time I plug a number in for x, any real number that I'm going to plug in for x, I'm always going to get a unique output value. So there's no values that are undefined in this function, like whatever I plug in for x and cube it, multiply by negative 4 and subtract by 1, I'm always going to get a unique y value, back out. So therefore, this is going to be, the domain here is going to be from negative infinity to infinity. Every single number, every real number between negative infinity and to infinity, I can plug in for x, and I am going to get out a y. So therefore, it is defined for all real values. Now we get into one of our main constraints, and one of those main constraints is dealing with the square root function. And it really could be any even root function, but mostly we're just going to focus with the square root for this class. So the restriction that we're talking about with the square root function is you can't take the square root of a negative number in the real number system. That's going to now push you to the complex number system. So under the radicand, so we have the square root and we have the radicand. Let me zoom in now. So when we're looking at the square root and the radicand, we know that the radicand has to be greater than equal to 0. So all we're going to want to make sure when we're doing a problem, when we see a radical, is set the radicand, so in this case it's 2x plus 3, set it greater than equal to 0. And that's going to represent the values that are always going to be positive. That will represent our domain, because any values for x that make my radicand negative are not going to be a domain. So now I just need to solve for x to determine those values. So I'll subtract by 3. Zoom in one more time. Subtract 3 on both sides, and then I'll divide by 2. And in this case, now I have x is going to be greater than or equal to a negative 3/2. So what that means is all numbers that are larger than or equal to negative 3/2 is going to make this radicand positive. That means it's going to be within the domain. So to write the domain, sometimes, what we did talked about in class was creating a number line for our domain. So let's just see, let's make here 0. Negative 3/2 is between negative 1 and negative 2. Okay. Now again, x is greater than or equal to, so therefore it can equal negative 3/2. So there's negative 3/2. All right. And it's all numbers that are greater than. So that's going to be all values to the right. And it's going to continue, right? But any number to the left or negative of negative 3/2 is not within the domain. So negative 3/2 is contained within our domain. So we're going to use a bracket to represent that. And then it's going to continue all the way going to more positive values of infinity. All right, looking at the next example brings into our next restriction, and our next restriction is you can't divide by 0. So what we want to do in this case is we understand that all the values are going to, all real numbers are going to work for this equation. Any real number that we plug in, we're always going to get an output, except for the values that make our denominator 0. So rather than try to find all the values that are in our domain, it's easier in this example to just find the numbers that are not in our domain. So we see this negative up here. And again, the negative could be in the numerator, denominator. It doesn't really, it's not going to affect our values here in this case. So I just want to make sure that we want to find the values where this denominator is going to be 0. So what we'll simply do is just take this 7 minus 2x and then set it equal to 0. Because we basically want to be able to find the values that are going to make my denominator equal to 0. So I can just add a 2x to both sides. And now I have 7 equals 2x. Divide by 2. And then again, that's like 3.5, right? If you're writing it as a decimal, so we could say, x equals 3.5. So again, now it's important for us to understand that what exactly is the understanding here of this 3.5 or this 7/2. Again, when you plug that number in for x, so let's just use the fraction, actually 7/2, it's easier. Actually, I don't know why I wrote 3.5. I hate decimals. I don't ever use decimals, nor do I expect my students to use decimals, so why am I using decimals? So let's just use 7/2. Okay, so when I plug 7/2 back into x, though, negative 2 times 7/2 is now going to be a negative 7, and 7 minus 7 is 0. Therefore, that makes my denominator now equal to 0. So what that means is my domain is going to consist of all real numbers except for 7/2, because that's what makes my denominator 0. So if I was going to use my number line approach, again, 7/2 is 3.5, so it's between 3 and 4. So we can say 7/2 right here. But it's undefined. So we're going to use a open circle. Now, all real numbers, less than and greater than 7/2, though, are going to be within the domain. So I'll shade for all reasons that way. Now, when you're dealing with a domain, let me just check here. Let's see in this. Okay. Now, when we're checking with the domain that has a discontinuity in it, where it's kind of like broken apart, what we can do is just find the domain to the left of 7/2 and then find the domain to the right of 7/2. So if I just wanted to find the domain of this left side of this little undefined value, I can see that it's all values to the left, so that's going to be decreasing from negative infinity, and then it's going to go all the way to 7/2, but again, 7/2 is undefined, so rather than using a bracket like I did here, I'm going to use an open circle. So I'll just do 7/2, and then I'll leave that as an open circle. Then, to the right of my undefined value, you can see that this domain is starting at 7/2, right? But it's undefined, and then it's going to continue for more and more positive values, which is going to continue to positive infinity. And then we can just combine these two domains together by using the union symbol. All right, so now let's kind of get into some examples here where now we have a radical in the denominator. So there's a couple different, points here. We're dealing with the constraint that you can't take the square root of a negative number, and we're also dealing with the constraint that you can't divide by 0. So you could start off by saying, all right, well, I know that I have to have my radicand has to be greater than or equal to 0, as well as my denominator. I want to figure out what values make that equal to 0. So you set your denominator equal to 0. And that's basically the same process you would apply for all of these types of equations where you're dealing with the radical and the rational function. So to solve this, now before I actually even get to solving, there's an issue with me writing x minus 1 is greater than or equal to 0, because when I write it as greater than or equal to 0, I don't want it to be equal to 0, right? I just want it to be greater than 0. So what I'm going to do is I'm going to erase this. Oops. To just write greater than 0. So what that means is that means I don't have to worry about defining when the function is equal to 0 for the denominator, because I'm just going to look for values that are greater than, not equal to 0. And therefore, I'll add 1 to both sides, and therefore, x has to be greater than 1. Now, if you wanted to solve this, I will just kind of solve it, and you can see. Let's just pretend you're not really following me there. So therefore, you solve it. X minus 1 is equal to 0, and then you add 1 to both sides. And you see that, oh, when x is equal to 1, the function is undefined, right? And that makes sense. Like, you look at 1, 1 minus 0 is 0. So if I would have had it included, if I would have kept that inequality symbol, it would have said x is greater than or equal to 1. But I don't want it to equal 1 because that makes my denominator 0. So we're just going to leave this as an undefined value. And basically now all I need to do is graph x is greater than 1. So I'll go ahead and get another number line. And I will go at 1. And since x is greater than 1 but not equal to, again, it's going to be an open circle. And values of x that are greater than 1 are going to be going to the right. And just like that. All right. Now, again, to write this as interval notation, my 1 is not defined for the function, so we're going to use a parenthesis. And that's going to continue to positive values, which will be infinity. All right. Now let's look at the next equation, which is another rational function. And in this example, same here, you can see we have a quadratic. So it's not as simple as just saying, you know, over here, well, even this was a fraction. It wasn't that like fun. But a lot of problems, like for this, you can say, oh, what number makes it denominator 0? Oh, that's 0. Like sometimes it's kind of obvious. Here, we're going to have to do a little factoring practice, which is perfectly fine. I mean, it happens. This is what we're going to have to come up to. So whenever we see a quadratic trinomial, a lot of times we just think, you know, all right, let's factor this and let's see what this would look like in factored form. So I'm just immediately going to rewrite my quadratic in factored form. So what two numbers multiply to give me -5, add to give me -3. Looks like that's going to be x minus 5 times x plus 2. Okay, so I'm just going to rewrite this as that. Done. All right, so basically, again, we want to find, there's no radical here, so we just want to find what values then make my denominator equal to 0. So I'm just going to set the factored form equal to 0. So I'll have this, I'll just move it equal to 0. And then again, remember from quadratics, if you have a term factored, which we do now, factored equal to 0, you can now just apply the 0 product property to go ahead and find the 0. So set each factor equal to 0, and now you can solve. X equals 5 and x equals -2. But again, when what that means then is when x equals 5, the denominator is 0. When x equals -2, the denominator is 0. So those values, 5 and -2, are not within the domain. So my domain is all real numbers except for +5 and -2. And if you want to verify this, just plug those numbers into your quadratic in the denominator and make sure they give you 0. All right, now working into this next example, now working into the next one. So if we're going to graph this, we have an undefined value at -2, and we have an undefined value at 5. So that means all values to the left of -2, all values between -2 and 5, and all values greater than 5. So again, writing the domain, just write the domain of each separate kind of section. So my domain would be from -infinity to -2. Again, I'm going to use parentheses for all of these because none of these values are defined. Infinity is not really a number that can be defined, so therefore that's why I use parentheses. And then I'll just connect this with -2 to 5, and then connect that with 5 to infinity. Done. All right, next example. So in this example, we have, we already know, like if you set the denominator equal to 0, you see that, oh, x cannot equal 0. So you know what, I'm just going to kind of simplify that and say, all right, rather than doing all that work, I know when x equals 0, that's not in the domain, because I want to focus on this one, 2 minus 2x. So again, we have a radical, so we know that our radicand has to be greater than or equal to 0 for our domain. So I'm going to take my radicand, and I'm going to set it greater than or equal to 0. And I can set it greater or equal to 0 because it's in the numerator. When it's in the denominator, I don't want it to equal 0. Now, in this case, you could just add the 2x and then solve it. I'm just going to use inverse operations just because one of those inequality rules that a lot of us kind of forget as time goes on is to remember to multiply, or when you multiply or divide by a negative number, to flip the sign. So x is going to be less than or equal to negative 2 divided by negative 2 is a positive 1. Okay, so this is important because x is all, so the domain right now for this restriction is all values less than or equal to 1. But we also know over here, x cannot equal 1 because that makes the denominator equal to 0. So we have our two restrictions. We have the restriction from the denominator and we have the restriction from the radical. So we got to make sure when we have multiple restrictions that we are finding the intersection or the combination of them both. So it has to apply for both of them. So in this example here, I'm going to go to 1, and that's going to be all values that are less than or equal to 1. But I can't have at 0, it's undefined. Okay, so my domain in this case would be from negative infinity to 0. Again, 0 is undefined, so it's parentheses. And then I'm going to go from 0 to 1, but I'm going to use a bracket here because 1 is defined. So there you go, ladies and gentlemen. That's kind of like the basics, at least as far as, from these functions. And really the main restrictions that we talked about in my class was really you can't take the square root of a negative number because we're mostly just dealing with square roots. So you can't take the square root of a negative number and you can't divide by 0. So to help you find the domain, set the radicand greater than or equal to 0 and set the denominator equal to 0. For all the other functions, if they don't have a radical or if they don't have a denominator, then we are going to, for at least now, the functions we're dealing with are going to be all real numbers. So we'll get on to later functions where they're still going to be restricted, but it's not restricted with a denominator or a radical. That's for later. All right, so now let's go and talk about the discontinuities of the graph. And basically what we've looked at from the graphical approach is a discontinuity being a hole, a jump discontinuity, and a vertical asymptote. And for the sake of dealing with just rational functions, we're only going to deal with a vertical asymptote and a hole. And really the difference between those two is how we describe those discontinuities as removable or non-removable. And the way, as when you look at the graph, the vertical asymptote is the value where the graphs are going to be approaching but never reach as far as vertical asymptotes. And a hole is really just kind of like a missing portion of the graph, like a hole in the graph. But the way that we describe them doesn't really make as much sense when you look at the graph. And what I'm meaning by like a hole is what we call a removable discontinuity. And a vertical asymptote is what we call a non-removable. So that makes more sense when we look at the algebraic understanding of our discontinuities. So in this example, you can see we have some discontinuities, right? We have a rational function. We know there's going to be values that are going to make the denominator equal to 0. But not all values that make the denominator equal to 0 are really the same graphically. So I didn't provide the graphs, but if you graph this, you'll kind of see. But the also tough thing about using graphing technology is they'll show you the asymptote, or at least you'll see where the graph is approaching, but they don't really show you a hole in the graph. So that's why it's really helpful to understand this algebraic approach. And really the first thing we want to do is simplify the function. So if I go ahead and simplify this function, I can't really do anything in numerator, but I can factor out an x here. And when I factor out an x in my denominator, I get an x minus 1. Okay, now if I was to continue simplifying this, you can see that the x's, or actually, well, hold on, let's stop right there. If I just wanted to find where are my discontinuities, then I'm going to set my denominator equal to 0, right? So I'd say x times x minus 1 equals 0, because this is actually important because this happens a lot. So I say, all right, I have x equals 0, x minus 1 equals 0, so therefore x equals 1. So now I have a discontinuity, two values that are not in the domain, 0 and 1. Right? But are they the same? Well, no, because the zero product, or not the zero, but the division property says that x divided by x is just 1, just like 3 divided by 3 is 1, right? So these can be divided out. So this graph can actually, or this function can actually be simplified to 1 over x minus 1. But it's important, just because you can simplify it doesn't mean these discontinuities go away. It just means we can classify them differently. When a discontinuity can be divided out, hence x minus, see the x here, that got divided out. So x equals 0 is what we call a removable discontinuity. because it got divided out. Whereas x minus 1 remains in the denominator. So the discontinuity, or the value that's undefined, x equals 1, is where the vertical asymptote. So that'd be a non-removable. Okay? So when we're looking at this, it's still a discontinuity. It's still an undefined value of the function, but if it can be divided out, it's removable and called a whole. And if it's non-removable, then it's going to be, or if it cannot be divided out, it's non-removable and a vertical asymptote. All right. So the removable gets divided out, non-removable does not get divided out. And really the main thing we're looking at is finding the values that make the denominator 0. That's where the discontinuities come, and then simplifying them to see what divides out. So typically what I like to do, which I didn't do in the last example, is I see my denominator and say, all right, let's just find the discontinuities. Let's find the values that are undefined for my function. So x squared minus 5x minus 6 equals 0. I need to factor this. What two numbers multiply to give me negative 6, but then also add to give me negative 5? Well, that's going to be x minus 6 and x plus 1. So I'm just going to skip the zero product property and know that my values that are undefined for my function are x equals 6 and x equals negative 1. So, but these are both undefined values, but are they the same discontinuity? So what we want to do now is simplify this to see if any of these divide out. Well, I already factored this. So I have x minus 2 all over x squared minus 5x. Oops, I want to write the factored form of that. So I have x minus 6 and x plus 1. Okay, and in this example, you can see that my discontinuity, neither my x minus 6 nor my x plus 1 divide out. So therefore, these are both going to be vertical asymptotes. So I am just going to say both vertical asymptotes, and they are also non-removable. All right, into the next one. I guess I really like to go ahead and do this one. Oh, well, this one, yeah, I see what I do here. So in this example, what we're doing is we're looking at x squared minus 4, x squared plus 1. So if I set my denominator equal to 0 to find my discontinuities, so I have x squared plus 4 equals 0. Well, when I go ahead and solve, I subtract a 4 on both sides. I get x squared equals negative 4. And when I take the square root of both sides, what I notice is under the real number system, I can't take the square root of a negative number, right? So that's going to cause imaginary numbers. Now, let me go back to my directions. Did I take into account this so people would know what I was doing? So identify the discontinuity of the function and then determine their domain. Oops, well, okay. I probably should have left something out that it could be a continuous function, because this function is defined for all values. And again, like, think about it. Think about plugging in a number in for x, like squaring it and then adding 4. You're never going to get to 0, right? Because whatever number you plug in, it's always going to be squared, so it all be positive, and then you're adding it to another positive value. So this is just a continuous function. Yeah. So we would say this is continuous, and the domain is from negative infinity to infinity. All right? All right, next example here. Now, this one is really, really important. I really like this one. So in this example, again, we see the denominator, so I'm going to set the denominator equal to 0. Now, you could just go ahead and solve, and that's perfectly fine. Add 4, divide by 4, right? The way that I'm going to do it is I'm going to factor out a 4. Now, let's just do it the way we would do it. I mean, you're just going to add 4, right? Okay. I mean, we're not going to make up some math or math knowledge, although that would be pretty cool, but I'll still address the point here in a second. So x equals 1 is the only number that is not in my function, right? That's the only number that makes my denominator equal to 0. So now we have that knowledge over discontinuity. Is this a whole or is this a asymptote? So the next thing we want to do is simplify. Well, I notice in my numerator, I can divide out a 2 in the numerator, and I can divide out a 2 in the denominator. Plus 1. Actually, I'm sorry, I can factor out a 4. Okay. Now, by factoring this out, you see that I can simplify this, right? This can be reduced to 1/2. And a lot of students will get this confused and they'll say, oh, well, 4 is a discontinuity too. No, that 4 doesn't make the denominator equal to 0. 4 is just a scalar that just got simplified to 2/4 got simplified to 1/2. But it's not a discontinuity. 4 is not a number that makes the denominator 0. So it's only the value that you can plug in for x that makes the denominator equal to 0. All right. So now let's go ahead and simplify this because we can simplify this more. What two numbers multiply to give you 1, add to give you negative 2x? Well, this turns into an x minus 1 times x minus 1, which is really a perfect square trinomial, right? And then we have an x minus 1. Well, now by using this division property, those divide out, so we're just left with x minus 1. So when we're looking into understanding this, we have one discontinuity at x equals 1. And we see that the discontinuity comes from x minus 1 being factored out. So therefore, that is removable, and this is a whole. Oh, did I forget to do the domains, I guess? I asked to do the domain. Oh, jeez. All right, I got to do the domain again. Dang it. All right, so I understand the point. The reason why I wanted to cover the domain here is because for you to understand that just because the vertical asymptote is remaining, the whole got divided out, the domain is still all values except for your discontinuity. So except for 0 and except for 1. So I'm going to kind of do that rather quickly because we kind of spent some time discussing everything else. So this would be negative infinity to 0, union 0 to 1, and then union, oops, not union, and then union 1 to infinity. Okay, let's look at the next one. Next one, my domain is I have two vertical asymptotes, so therefore it's going to be from negative infinity to negative 1, union negative 1 to 6, union 6 to infinity. Hopefully it's okay with you guys that we already kind of went through this. Or we already kind of went through describing. So continuous, I already did that one. And then this one, we only have a whole at 1. So it's going to be from negative infinity to 1, union 1 to infinity. Okay, so now let's just go and touch base on the multiple choice functions, and just so we can kind of describe them, and then I'll do a little bit of Q&A just if you guys have any questions as I kind of wrap this up. Anything you guys are working on in your own classes or in questions about this topic here. So this one says find the domain of the function f of x is square root of x and x minus 1. So automatically I know that x cannot equal 1, so 1 is not going to be in the domain. So I know that one doesn't work. That one could, that one could, that one could. Okay, so, and this one's from 0 to infinity, so that one's not going to work. All right, and then this one is square root, so therefore square root of x, that means all values that are greater than 0. So, it has to be basically all positive values, right? So it has to be all positive numbers, so that works. That's from 0 to 1, so like 4 is in the domain, so that's not it. But this one doesn't include that. So x is greater than 1, good. But what about like 0? Like 0 is in the domain. This doesn't cover being 0. This just, or like 1/2. 1/2's in the domain. So this one from 0 to 1, 1 to infinity is going to be our correct answer. All right, the next one. Let g of x equals 5 over x minus 4. Find the domain of g. So again, I'm basically looking at this, and I only see a rational function. So I'm saying what numbers make my denominator equal to 0, and that's going to be 4. So 4 is not in the domain. So I know that doesn't work. That one doesn't work. And then I kind of see the difference here. Well, this one's saying negative 4, but remember, we can double check that by setting the denominator equal to 0. And by setting the denominator equal to 0, you can see it's positive 4 is what makes the denominator equal to 0. So that's why that one doesn't work. Okay. Determine the equation of a vertical asymptote. So again, remember, if you're graphing a vertical asymptote, like for instance, here's 1, that's a vertical line, right? So it's a vertical line at the x value of 1. So this would be x equals 1. So vertical asymptotes are, first of all, going to be in the form of x. So that one doesn't work. And then we got to look at, well, where is the function undefined? Well, the function is undefined when the denominator is equal to 0. What is the only value that makes the denominator equal to 0? That is d. Okay. And then last but not least, find the points of discontinuity. So that can be holes, that can be asymptotes, anything, right, that makes the denominator equal to 0. And the only values I see that make the denominator equal to 0 are 3 and 5. Now, the 5s divide out, but who cares? It's still a discontinuity. That just means that's a hole, and x equals 3 is going to be an asymptote. All right, but they're still both discontinuities. If x was in the denominator, then we'd include 0 as another discontinuity. But since x is in the numerator, it's not affecting the domain. We're only looking at the discontinuities is the values that are undefined for the domain. So therefore, C would be the answer there. And then for the challenge problems, basically, break these up. Break to go ahead and find the domain of each and every one of these sections, and then graph them using the number line and trying to find the intersection of them. So I will have the answers provided, but I'm not going to work them on the live stream. So there you go. Hope you guys enjoyed. All right, so now let's go ahead and see some question and answers. Anything you guys have, I only have about 10 minutes, but if I have some questions I can help you out with. For those of you that have stayed for my homework session, I would love to help you guys out. Let me just kind of see see where we got going on. So, hey, Max, thanks, man, just helping out. Just want to see if you guys are here. So if you guys do have any questions or if you want to add anything, just make sure you let me know. Hey, Andres. And yeah, I don't have anything calculus. Unfortunately, I'm not teaching calculus this year. I'm only teaching pre-calculus. So I'm not going to have as much calculus content coming out this year. Hey, Timothy. Well, man, happy to help teaching pre-calculus back again. And if you're taking calculus, I do have, some more videos, coming up, or more videos I did last year. Can't we apply lowest point equals opposite of b divided by 2a? Yeah, that's where, when you're looking at a quadratic, that's going to be where your vertex is going to lie on, the opposite b divided by, or negative b divided by 4a. No, that's a different point. I don't really remember. I'd have to go back and look because it's been a while since I taught any of that. So, Orange Sisters, just want to say thanks for all your help. Orange Bats, your videos are very helpful. Well, I'm very happy to be able to help you out and, answer any kind of questions you guys have. Just to let you guys know, this is like one of my down times as far as, people looking on the, or watching my videos. So this is, it's good and bad. Like, one, I'm probably not reaching as many people as my channel as I could if in case I was doing this at like 9 or 10 o'clock at night. But on the other side, for those of you that this time frame does work, it's very good for you to be able to submit some comments and ask some questions that I can basically, I'm not going to be overloaded with, because I know when I did this at like 10 o'clock on like a Wednesday, I would just get too many questions and I wasn't able to really answer everything. So this is the time frame that I'm going to plan on doing. I'll probably do a live stream like at least once or twice a week. So if you want to be notified of my upcoming live streams, make sure you just hit that bell notification and you can get updates, because I will try to plan ahead my live streams as much as possible, but I can't guarantee that I'm going to, be able to say, hey, I'm going to go live stream on Tuesday or on Thursday and then be able to follow through. So it's usually going to be like a kind of game day call, but I will develop a little bit of system for you guys to be able to ask questions if you guys start getting your questions coming in, and therefore you guys can go ahead and submit them. So, sweet. All right. Hey, Brock. Gopal says, find all the solutions of the equation in the interval 0 to 2 pi for negative 3 cosecant of theta, 20. Write your answer in radians in terms of pi. If there's more than one solution, separate them with commas. Please help me solve this. Oh, man, we haven't gotten a trig yet, so I'm not brushed up, but I'm not sure exactly what your equation is. Negative 3 cosecant of 2 theta. I don't know what exactly your question is, Gopal, so I don't really know or what the exact equation is. So if you can help me out with that, I will remember as far as in the sign, I can help you out a little bit, working through them, but I kind of need to know exactly the right equation is so I can kind of properly give you some advice. So besides that, I'll probably just end this stream unless I get a little bit more information. But if you guys have, any other questions or anything else you guys like me to address on the live stream, I am thinking about doing some more live streams that are not centered around me doing homework, but maybe just really kind of focusing on doing some questions for you guys. So if you do have some tips or maybe some advice that you throw my way as far as what you'd like to see on some live streams, especially for those of you that this time frame works, then let me know in the chat and I'll be more than happy to help. So, well, unfortunately, Gopal, I'm gonna have to go. I don't really I got to get back home now. So if you just want to make sure, I will plan on being either live again tomorrow or on Thursday. So Gopal, if you just want to plan on that this week, and make sure you have that question ready. Final solutions, I know, but I don't know your equation. So I don't know what the exact equation is that you wrote. So if you'll plan on giving that, send that over. Make sure you have that ready for tomorrow or on Thursday. I don't know which day I'm going to go live, but I'll be prepared to help you out with that answer. All right. Sorry, I can't help you out more with this, but I'll make sure I cover it on Wednesday or Thursday. So cheers, guys. I'll see you guys then. Oh, wait.